Hello, in this lecture we'll answer two questions. In the first question, we find out the area of this rectangle ABCD, and in the second question, we will find out the area of this green shape that is inside square ABCD. So we'll start with the first question. In the drawing, we have rectangle ABCD. Inside this rectangle, we have this semicircle. In addition, we know that this is a code AP that is equals to 6 units in its length. This is line 7 PC that is equals to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So because of the fact that ABCD is a rectangle, all those four angles are right angles. So this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. In the next step, we'll define the center of this semicircle. This point is point O. We'll define the radius of this semicircle as x. We will define the tangent point of this semicircle with side AB of this rectangle. This point is point E. And finally, we define the point of tendency of tangent DC with this semicircle. This point is point M. And we will join points O and M together by a straight line. Point O is the center of this semicircle. Point M is the point on the semicircle itself. Therefore, OM is the radius of this semicircle that is equal to x. Likewise, OE is also the radius that is equal to x. And OA is the radius of this semicircle that is equal to x. Because of the fact that the radius OM that is equal to x, the radius OM is drawn to point M, that is the point of tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. By doing this construction, we can do quadrilateral DMOA. Inside this quadrilateral DMOA, we have 2 right angles. The sum of right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces again, in total it must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 pieces again must be equal to 90 degrees in its size. So inside quadrilateral DMOA we have 4 angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we have to this quadrilateral ADMO is rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ADMO, side MO must be equal to the opposite side DA. But MO is x, therefore DA must be also equal to x units in its length. In the next step, we will join points P and E together by a straight line. And we know actually that ABCD is a rectangle, and the opposite sides of a rectangle are equal to each other. That is to say, side AD is equal to the opposite side CB. But AD is x, therefore CB must be also equal to x units in its length. And then we join points P and E together by side line. By joining points P and E, we get the peripheral angle APE. This is peripheral angle APE. Peripheral angle APE subtend on AE, that is the diameter of this semicircle. And according to rule 7, any peripheral angle that subtend on the diameter of the circle or semicircle, it must be equal to 90 degrees in its size. So, let's quickly to rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees. So in the drawing we have a circle. This is called AB. That is defined as the diameter because it passes through point O. That is the center of this circle. So AB is the diameter of this circle. This is peripheral angle ACB that subtends on AB, that is the diameter of this circle. And according to this rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. Therefore, peripheral angle ACB is a right angle. It is equal to 90 degrees in its size. So, as I already mentioned before, we can implement rule 7 in our drawing. Why? Because in our drawing, this is peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and therefore, according to rule 7, the size of peripheral angle APE is must be equal to 90 degrees in its size. In the next step, we define this angle as alpha. So in the right triangle AP, this angle equals to alpha, this angle equals to 90 degrees, therefore this furthest angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the right big triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this furthest angle, this furthest angle must be equal to 90 degrees minus alpha. According to the symbol that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that the right big triangle ABC is similar to this one, right triangle APE. So write it down. We prove that the right big triangle ABC is similar to the right small triangle APE. So, why those two right triangles are similar to each other? First of all, this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the big triangle ABC, and angle A also belongs to the small triangle APE. So we can write down that angle A equals to itself is a common angle that belongs to both triangles. So if we relate to this angle, angle A, as it belongs to the big triangle ABC, it will be defined as angle CAB. And angle A equals to itself. So if we relate to this angle, angle A, as it belongs to the small triangle APE, it will be defined as angle EAP. So actually, this equation means that angle A equals to itself. we just call to angle A two different names. Angle A equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and the both are equal to each other. So actually this is angle ABC. In the right triangle ABC, and it is equal to this angle, that is actually angle APE. In the right triangle APE. So repeat again. We actually found out that angle ABC in the right big triangle ABC is equal to angle APE in the right small triangle APE. They are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus 1 and therefore they are equal to each other. So actually this is angle ACB. The right big triangle ACB, it is equal to this angle, that is actually angle AEP. The small right triangle APE. I'll repeat again. I actually found out that angle ACB in the right big triangle ABC is equal to angle AEP in the small right triangle APE. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. Now I can prove that all the triangles of the right big triangle ABC are correspondingly equal to all the triangles of the right small triangle APE. Therefore those two right triangles are similar to each other according to angle similarity rule. So write it down. So if we prove that the right big triangle ABC is similar, this is the sum of similar, to the right small triangle APE, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the small right triangle APE over side AB of the right big triangle ABC is equal to side AE of the right triangle AEP over side AC of the big right triangle ABC. So repeat again. We will derive that side AP of the small right triangle APE over side AB of the big right triangle ABC is equal to side AE of the small right triangle APE over side AC of the big right triangle ABC. AP equals to 6 over AB. AB is the missing side, so we will leave it as it is. And it is equal to AE. AE is the diameter of this semicircle, it is equal to 2x. Over AC. AC in total equals to 6 plus 5, that is 11. So in total, we found out that 6 over AB equals to 2x over 11. Here, we will cross multiply this equation, and we will get that 6 times 11 is 66, so 66 equals to 2x times AB. So here we will divide this equation by 2, and we get that 66 over 2 is 33, so 33 equals to 2x over 2 is x, so in total this expression equals to x times AB. Here we divide this equation by x, and finally we get that AB equals to 33 over x units. So the length of this side AB of heptagon ABCD is equal to 33 over x units. Our mission is to find out the area of this heptagon ABCD. So what is the area of heptagon ABCD? Actually, we know that the area of an heptagon equals to the length of the heptagon times the width. And therefore, the area of this heptagon ABCD must be equal to the length of this heptagon ABCD over times the width. The length is AB, and the width is DC. So in total, we found out that the area of heptagon ABCD equals to AB times DC. AB is 33 over x. DC is x. 33 over x times x is 33. But we have x in the numerator and x in the denominator, so x will get cancelled. And we left only with 33. So in total, which we found out the area of this heptagon ABCD is equal to 33 square units. So we finish with the first question. In the next step, I present to you the second question, and we'll solve the second question of this lecture. Our mission in this second question is to find out the area of this green shape. So in the drawing, we have square ABCD. In addition, we know that line segment BP equals to line segment PC. This is target this is target OPC. This is equal to 5 square units in its size. Again, our mission is to find out the area of this green shape. So first of all, we define the length of this line segment BP is A. Because of the fact that BP equals to PC and BP equals to A, therefore PC must be also equal to A. So in total, BP plus PC is A plus A, that is 2A, and we know that all the sides of a square are equal to each other. Therefore, AD must be also equal to 2A units in its length. Those angles are defined as vertex angles. We know that vertex angles are equal to each other. So if the size of this angle is theta, then the size of this angle must be also equal to theta, because they are equal to each other according to the rule that I mentioned. We know that the opposite sides of a square are parallel to each other. Therefore, in this square ABCD, side AD is parallel to the opposite side BC. Those two angles are defined as alternating angles, and they are located between the parallel lines AD and BC. And therefore, those two angles are equal to each other and their sizes according to rule 15. If the size of this angle is alpha, then the size of this angle must be also equal to alpha according to rule 15. Rule 15 states that alternating angles between parallel lines are equal to each other. So those two alternating angles are located between the parallel lines AD and BC, therefore they are equal to each other. So if the size of this angle is alpha, the size of this angle must be also equal to alpha according to rule 15. Likewise, those two angles are also defined as alternating angles and are located between the same parallel lines AD and BC, and therefore they are equal to each other according to rule 15. So if we define the size of this angle as beta, then this angle must be also equal to beta because they are equal to each other according to rule 15. Actually, all the angles of the big triangle ADO correspondingly equal to all the angles of this small triangle COP. Therefore, those two triangles are similar to each other according to angle similarity rule. In both triangles we have angle theta, in both triangles we have angle alpha, and in both triangles we have angle beta. So I write it down. Just we found out that the big triangle ADO is similar, this is the sign of similar, to the small triangle COP, according to angle similarity rule. So in the next step, I will present to you a new rule in relation to two similar triangles, and we will implement the new rule in our drawing in those two similar triangles AOD and COP. The new rule is rule 22. According to the new rule, rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So in the drawing we have two triangles, triangle ABC and triangle DEF. Those two triangles are similar to each other, and according to this rule 22, the ratio between the areas of those two triangles is equal to the square of the ratio between their corresponding sides. So, what is the ratio between the areas of those two triangles? It is the area of triangle ABC over the area of triangle DEF. And that ratio, according to this rule 22, that ratio is equal to the sum, to the square of the ratio of their corresponding sides. What are the corresponding sides of those two triangles ABC and EDF? Side AC is the corresponding side of side DE. Likewise, side AB of triangle ABC is the corresponding side of side DE. And finally, side CB is the corresponding side of side EF. So the square of the ratio of their corresponding sides is AC over DE squared. Likewise, it is also AB over DEF squared. And finally, it is CB over EF squared. So the ratio between the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. We can implement the new rule in our drawing. Why? Because in our drawing we have already found out that the big triangle DOA is similar to the small triangle COP. And according to rule 22, the ratio between the areas of those two similar triangles is actually, the ratio is the area of triangle ADO, the big triangle ADO, over the area of this small triangle OCP. So actually, this expression is the ratio between the areas of those two similar triangles, and that ratio is equal to the square of the ratio of their corresponding sides. Side AD is the corresponding side to side PC. Why side AD is the corresponding side to side PC? Because of the fact that side AD is located in front equal theta in triangle ADO, and side PC is also located in front of this angle theta in triangle COP. Therefore, side AD is the corresponding side to side PC. So it is AD over PC squared. The square of the ratio of their corresponding sides is AD over PC squared. So this equation is the implementation of Rule 22 in our drawing. The area of this triangle ADO is unknown, so we will leave it as it is. This is the area of triangle ADO. Over the area of this triangle OCP. It is given as the equation that the area of this triangle OCP is equal to 5 square units. So we substitute the area of triangle OCP by 5, and it is equal to AD. AD is 2A over PC. PC is A. We have A in the denominator and A in the denominator, so A will be cancelled, and we left only with 2. It is squared. I forgot to square it. It is 2A over A squared. So we have A in the denominator and A in the denominator, so A will get cancelled. And we left only with 2 squared. 2 squared is of course 4. So total we found out that the area of triangle ADO over 5 equals to 4. Here we multiply the equation by 5. And we get that the area of the big triangle ADO is equal to 5 times 4, that is 20 square units. So the area of this big triangle ADO is equal to 20 square units in its size. Because of the fact that triangle ADO is similar to triangle POC, the following relationship exists between their sides. Side AD of triangle ADO over side PC of triangle POC is equal to side AO of triangle AOD over side OC of triangle POC. And again, from the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AO of triangle ADO over side PC of triangle POC is equal to side AO of triangle ADO over side OC of triangle COP. AD is 2A over PC. PC is A, and it is equal to AO. We have already found out that it is equal to AO over OC. Read again. AO is 2A, PC is A. AD is 2A, PC is A. AO is unknown and OC is unknown. We have A in the numerator and A in the denominator, so A will get cancelled and we left only with 2. So we found out that 2 equals to AO over OC. Here we multiply this equation by OC, and we get that 2 times OC is equal to AO. 2 times OC equals to AO. So if we define the length of side OC as B, and we substitute OC by B in this equation, we get that 2 times B equals to AO. 2 times B equals to AO. That is to say, we found out that the length of side AO is twice as long as the length of side OC. So this is side OC. If side OC equals 2 units in its length, then side OA equals to 2 units in its length. Okay? So in the next step, I'll present to you a new rule, and we'll implement the new rule in our drawing. The new rule is Rule 23. Rule 23 is true in any triangle. So this is triangle ABC. That could be any triangle. This triangle ABC, if we draw the red line segment AP, the red line segment AP will divide this triangle ABC into 2 smaller triangles. The first small triangle is ABP, and the second small triangle is APC. According to this rule, Rule 23, the ratio between the areas of those 2 small triangles is equal to the ratio between their corresponding bases. So the area of this triangle ABP equals to the base, that is BP, times the height, that is h over 2. Again, the area of this triangle ABP equals to the base BP times the height h over 2. Likewise, the area of this small triangle APC is equal to the base PC times the height, that is h. Both triangles have the same height, h, divided by 2. Repeat again, the area of this small triangle APC is equal to the base PC times the height h over 2. And the ratio between the areas of those 2 small triangles is the ratio between those 2 expressions, of course. Again, the ratio between the areas of those 2 small triangles is BP times h over 2 over CP times h over 2. We have in the numerator and the denominator of this expression 1/2, so 1/2 will get cancelled, and we also have h in the numerator and h in the denominator, so h also will get cancelled, and we're left only with BP over CP. So in total, we found out that the ratio between the areas of those 2 small triangles that were created by drawing the red line AP, the red line segment AP, the ratio between the areas of those 2 small triangles is equal to the ratio between their bases. Why it is equal to the ratio between their bases? Because BP is the base of triangle ABP and PC is the base of triangle APC. Again, so the ratio between the areas of the small triangles is equal to the ratio of their corresponding bases. So we can implement Rule 23 in our drawing. Why? Because in our drawing, this is the right triangle ADC. This right triangle ADC, we have line 7DO that divides triangle ADC into 2 smaller triangles. So therefore, all the requirements of Rule 23 are satisfied, and therefore we can implement Rule 23. According to Rule 23, the ratio between the areas of the small triangles that were created by line 7DO, the ratio between the areas of those 2 triangles is equal to the ratio between their corresponding bases. The base of triangle ADO is AO, and the base of triangle DOC is OC. So total, we actually found out that the ratio between the areas of those two small triangles is the area of triangle ADO over the area of this triangle, triangle DOC. And the ratio between the areas of those two smaller triangles is equal to the ratio between their bases, between their corresponding bases. The base of this triangle AOD is AO. The base of this triangle DOC is OC. And the ratio between their bases is of course AO over OC. So this equation is the implementation of Rule 23 in our drawing. And it means that the ratio between the areas of the smaller triangles that were created by line 7DO, the ratio between the areas is the area of the small triangle ADO over the area of triangle DOC, the small triangle DOC. And that ratio is equal to the ratio between their corresponding bases. The base of triangle ADO is AO, and the base of triangle DOC is OC. So it is AO over OC. The ratio between their bases is AO over OC. AO over OC. So the ratio between the areas of the small triangles is equal to the ratio between their corresponding bases. The corresponding bases is AO and OC. The ratio between their corresponding bases is AO over OC. Triangle, the area of this triangle ADO is 20, so we'll substitute the area of triangle ADO by 20. And over the area of triangle DOC. The area of triangle DOC is unknown, so we leave it as it is. So it is 20 over the area of triangle DOC, the small triangle DOC. And it is equal to AO over OC. AO is 2B over OC. OC is B. So here we have B in the denominator and B in the denominator, so B will get cancelled and we left only with 2. So in total we found out that 20 over the area of triangle DOC equals to 2. Here we multiply this equation by the area of triangle DOC, and we get that 20 equals to 2 times the area of triangle DOC. So here we divide this equation by 2, and finally we get that the area of the small triangle DOC is equal to 20 over 2, that is 10 square units. So we found out that the area of this small triangle DOC is equal to 10 square units. ABCD is a square, therefore all of its sides are equal to each other. For that reason, the area of triangle ABC, the right triangle ABC, actually triangle ABC can go into triangle ADC, according to side rule. Why they can go to each other? Because side AB of triangle ABC is equal to side DC of triangle ADC, because it is a square. Likewise, side BC of triangle ABC is equal to side AD of triangle ADC for the same reason. And finally, AC is a common side that belongs to both triangles. So AC equals to itself is a common side that belongs to both triangles. So in total, we have found out that triangle ADC can go into triangle ABC can go into triangle ADC according to side rule. So I write it down. the right triangle and triangle ABC. Congruent, this is the sign of congruent to the right triangle, triangle ADC, according to side rule. And from the fact that those two triangles can go into each other, we derive that they have also the same areas. That is to say, the area of triangle ABC, the right triangle ABC, is equal to the area of the right triangle, triangle ADC. Actually, any triangles that can go into each other, they must have also the same areas. But actually, the area of this triangle ADC, the area of this triangle ADC is equal to 20 plus 10, that is 30 square units. So you can write here that the area of triangle ADC equals to 30 square units, and from this equation, the area of triangle ABC equals to the area of triangle ADC equals to 30. We will derive that the area of triangle ABC is also equal to 30 square units from one side. But from the other side, if we define the area of the green shape, that is the area that we are looking for in this question, as x, that is to say, the area of the green shape is equal to x square units according to our definition. So in total, the area of the right triangle ABC will be equal to x plus 5 square units. So from the other side, the area of triangle ABC is equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We will derive that x plus 5 equals to 30. So here we subtract 5 from this equation, and finally we get that x equals to 30 minus 5, that is 25 square units. And that is the answer to the question. We found out the area of this green shape is equal to 25 square units. So in the next step, I will summarize the lecture. We'll start with the first question, of course. Our mission in this first question is to find out the area of this rectangle ABCD. So in the moment we have rectangle ABCD and we have this semicircle inside rectangle ABCD. In addition, you know that this is called AP, that is equal to 6 units in its length. This is called PC, that is equal to 5 units in its length. And then our mission is to find out the area of this rectangle ABCD. Because of the fact that ABCD is a rectangle, all those 4 angles are right angles. In the next step, we defined the center of this semicircle. This point is point O. We define the radius of this semicircle as x. We define the point of tendency of tangent DC with this semicircle. This point is point M. And finally, we define the touching point of this semicircle with side AB of rectangle ABCD. This point is point E. Point O is the center of this semicircle. Point A is the point on the semicircle itself. Therefore, OA is the radius of this semicircle. That is x. Likewise, OE is also the radius of this semicircle. That is equals to x. We join points O and M together by straight line. OM is of course the radius of this semicircle. That is equal to x. Because of the fact that the radius OM that is equal to x, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing this construction, we can deduce quadrilateral DMO. Inside quadrilateral DMOA, we have 1, 2, 3 right angles. The sum of 3 right angles is equal to 270 degrees. So 270 degrees plus the size of this fourth piece again, in total it must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth piece again must be equal to 90 degrees in its size. So inside quadrilateral DMOA we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we went to quadrilateral DMOA is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle DMOA, side MO must be equal to the opposite side DA. But MO is x, therefore the opposite side DA must be also equal to x units in its length. Likewise, if we focus on the big rectangle ABCD, the opposite sides must be equal to each other. That is to say, side AD must be equal to the opposite side CB. But DA is x, therefore the opposite side CB must be also equal to x units in its length. In the next step, we join points A and P together by straight line. By joining points A and P, we get that peripheral angle APE. This is peripheral angle APE that subtends on AE, that is the diameter of the semicircle, and we know that any peripheral angle that subtends on the diameter of the semicircle or circle must be equal to 90 degrees in its size according to rule 7. Therefore, this peripheral angle APE is equal to 90 degrees in its size. In the next step, we define this angle as alpha. So, in the right angle APE, this angle equals to alpha, this angle equals to 90 degrees. And therefore, this firmness angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right angle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this firmness angle must be equal to 90 degrees minus alpha. In the next step, we prove that the big right angle ABC is similar to this right angle APE. So why those two right angles are similar to each other? First of all, this is angle A, this is a common angle that belongs to both triangles. So we can write down that angle A equals to itself is a common angle that belongs to both triangles. Likewise, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we prove that all the angles of the right triangle ABC are correspondingly equal to all the angles of the right triangle APE, and therefore those two right angles are similar to each other according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side AP of triangle APE or side AB of the right big triangle ABC is equal to side AE of the right triangle AEP over side AC of the right big triangle ABC. So if again, we derive that side AP of the right triangle APE over side AB of the right big triangle ABC is equal to side AE of the right triangle APE over side AC of the right big triangle ABC. AP is 6, AP is the missing side, so it is. AE is the diameter of this semicircle, that is 2x, and AC in total it is 6 plus 5, that is 11. So in total we can find out that 6 over AB equals to 2x over 11. Here we cross multiply this equation, finally found out that 6 times 11 is 66 equals to 2x times AB. Here we divided this equation by 2 and finally found out that 66 over 2 is 33. So 33 equals to x times AB. Here we divided this equation by x and finally found out that AB equals to 33 over x. So side AB of rectangle ABC is equal to 33 over x units in its length. Our mission is to find out the area of this rectangle ABCD. So we have to find out the area of rectangle ABCD. Actually, you know that the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is CB. So in total, the area of rectangle ABCD must be equal to AB times DC. AB times CB. AB times CB. AB is 33 over x, and CB is x. So in total, ABCD equals to 33 over x times x. We have x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33. So in total, we found out that the area of this rectangle ABCD is equal to 33 square meters. We finished with the first question. In the next step, I presented to you the second question, and we solve the second question of this lecture. Our mission in this second question is to find out the area of this green shape. So in the drawing we have square ABCD, line 7 BP equals to line 7 PC. This is triangle POC, is equals to 5 units in its size. Again, our mission is to find out the area of this green shape. So first of all, we define line 7 BP as A. PC also, BP equals to PC, therefore PC must be also equal to A. You know that all the sides of the square are equal to each other. BC is A plus A, that is 2A, therefore AD must be also equal to 2A. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if the size of this angle is theta, then the size of this angle must be also equal to theta, because they are equal to each other according to the rule that I mentioned. We know that the opposite sides of a square are parallel to each other, so in square ABCD, side AD is parallel to side BC. Those two angles are defined as alternating angles, and they are located between the parallels AD and BC, and therefore they are equal to each other according to rule 15. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha, because they are equal to each other. Likewise, those two angles are also defined as alternating angles, and they are located between the same parallels AD and BC, and therefore they are equal to each other according to rule 15. If the size of this angle is beta, then the size of this angle must be also equal to beta, because they are equal to each other. So in total, we have found out that the big triangle AOD is similar to this one triangle POC according to angle similarity rule. In both triangles we have angle alpha, in both triangles we have angle theta, and in both triangles we have angle beta. So those two triangles are similar to each other according to angle similarity rule. In the next step, I presented to you rule 22, and we implemented rule 22 in our drawing. According to rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So in the drawing we have those two triangles ABC and DEF are similar to each other. And according to this rule 22, the ratio between the areas of those two triangles, that is to say, the area of triangle ABC over the area of this triangle DEF, is equal to the square of the ratio of their corresponding sides. In those two triangles, the side AC is the corresponding side to side DE, side AB is the corresponding side to side DF, and finally side CB is the corresponding side of side EF. So the ratio between the areas of those two similar triangles is equal to the square of the ratio of their corresponding sides. Here side AC is the corresponding side to side DE, so the square of the ratio of those two corresponding sides is AC over DE squared. Likewise, side AB is the corresponding side to side DF, so the square of the ratio of those two corresponding sides is of course AB over DF squared, and finally side CB is the corresponding side of side EF, so the square of the ratio of those two corresponding sides is of course CB over EF squared. So in total, according to rule 22, the ratio between the areas of two similar triangles is equal to the square of the ratio of their corresponding sides. So we can implement rule 22 in our drawing. When we look in our drawing, we have those two triangles that are similar to each other. So according to rule 22, the ratio between the areas of those two triangles is equal to the square of the ratio of their corresponding sides. Side AD of triangle ADO is the corresponding side to side PC. Why side AD is the corresponding side to side PC? Because side AD is in front of angle theta, and side PC is also in front of angle theta. So side AD is the corresponding side to side PC. And the square of the ratio of those two corresponding sides is of course AD over PC squared. So according to rule 22, the ratio between the corresponding sides of the two similar triangles is the area of triangle ADO over the area of triangle OCP. And it is equal to the square of the ratio between their corresponding sides. The square of the ratio between their corresponding sides is AD over PC squared. So the ratio between their corresponding, the ratio between the areas of the two similar triangles is equal to the square of the ratio between their corresponding sides. The ratio is the area of triangle ADO over the area of triangle OCP, and it is equal to the ratio between their corresponding sides. It is actually AD over PC squared. The area of triangle ADO is unknown, so we leave it as it is. The area of this triangle CPO is 5, so substitute the triangle CPO by 5, and we have AD over PC squared. AD is 2A and PC is A, so it is 2A over A squared. We have A in the numerator and A in the denominator, so A will get cancelled. So in total, this expression equals to, after cancelled A, it is equal to 2 squared, that is 4. So in total, we found out the area of triangle ADO over 5 equals to 4. If we multiply this equation by 5 and finally found out that the area of the big triangle ADO is equal to 20 square units. This is triangle ADO, the area of this triangle ADO is 20 square units. So those two triangles are similar to each other. Therefore, the following relationship exists between their sides. Side AD of triangle ADO or side PC of triangle POC is equal to side AO of triangle ADO over side OC of triangle POC. Repeat again. Side AD of the right triangle ADO, it is not a right triangle. Side AD of triangle ADO or side PC of the small triangle PCO equals to side AO of the triangle ADO over side OC of triangle POC. AD equals to 2A, PC equals to A, so it is 2A over A, that equals to OA over OC. We have A in the numerator and A in the denominator, so A will get cancelled and we left only with 2. So we found out that 2 equals to AO over OC. Here we multiply this equation by OC and finally found out that 2 times OC equals to OA. We define the length of line segment OC as B, so we substitute B, OC by B in this equation, and we finally found out that 2B equals to OA. So in total, we found out that if the length of this line segment OC is defined as B, then the length of line segment OA is 2B. That is to say, line segment OA is twice as long as line segment OC. So in total, OC equals 2B and OA equals to 2B. In the next step, I presented to you a new rule, and we implemented the new rule in our drawing. The new rule is rule 23. according to, first of all, rule 23 is true in any triangle. This is triangle ABC that could be in a triangle. So if you draw the red line segment AP in this triangle ABC from the vertex A, you will create two smaller triangles. The first triangle is ABP and the second triangle is triangle APC. And according to this rule, rule 23, the ratio between the areas of those two triangles is equal to the ratio between their corresponding bases. The base of triangle ABP is BP and the base of triangle APC is PC. So the ratio between the areas of those two triangles equals to BP over PC. That is the ratio between their corresponding bases. So the area of triangle ABP equals to the base BP times the height that is edge over 2. Likewise, the area of this triangle APC is the base PC times the height edge over 2. Both triangles have the same height that is edge. So the area of triangle ABP is BP times edge over 2. The area of triangle APC is PC times edge over 2. And the ratio between the areas is, of course, the ratio between those two expressions. And the ratio between those two expressions is BP times edge over 2 over CP times edge over 2. We have 1/2 in the numerator and 1/2 in the denominator, so 1/2 will get cancelled. Likewise, we have edge in the numerator and edge in the denominator, so edge also will get cancelled, and we left only with BP over CP. BP is the base of this triangle BPC, and PC is the base of this triangle APC. So the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. That is BP over PC. So we can actually implement rule 23 in our drawing. Why? Because in our drawing, if we focus on this big triangle ADC, we have here line segment OD that divides triangle ADC into two parts, into two small triangles. The first small triangle is triangle ADO, and the second small triangle is triangle ODC. So all the requirements of rule 23 are satisfied, and therefore we can implement rule 23. According to rule 23, the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. The base of this triangle is AO, the base of triangle ADO is AO, and the base of triangle ODC is OC. So the ratio between their bases is AO over OC. So the ratio between the areas of those two triangles is equal to AO over OC. So the ratio between the areas of those two triangles is equal to the area of triangle ADO over the area of triangle DOC. Again, it is the area of triangle ADO over the area of triangle DOC. And the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. Then the ratio between their corresponding bases is AO over OC. The area of triangle ADO is 20 square units, so substitute the area of triangle ADO by 20 over the area of triangle DOC. The area of triangle DOC is unknown, so we left it as it is. So in total, we found out that 20 over the area of triangle DOC equals to AO over OC. AO is 2B and OC is B. So total AO over OC is 2B over B. We have B in the numerator and B in the denominator, so B will get cancelled, and we left only with 2. So in total, we found out that 20 over the area of triangle DOC equals to 2. Here we multiply this equation by the area of triangle DOC, and finally found out that 20 equals to 2 times the area of triangle DOC. Here we divided this equation by 2, and finally found out that the area of the small triangle DOC equals to 20 over 2, that is 10. So the area of this triangle DOC equals to 10 square units. Here, the right triangle ABC can go into this triangle ADC according to side rule. So why those two right triangles can go into each other? First of all, side AB of triangle ABC is equal to side DC of triangle ADC, because ABCD is a square and all of the sides are equal to each other. Likewise, side BC of triangle ABC is equal to side AD of triangle ADC because of the same reason. And finally, side AC is a common side that belongs to both triangles. So we can write down that AC equals to itself is a common side that belongs to both triangles. So in total, we can find out the triangle ABC can go into triangle ADC according to side rule. So again, we can find out that the right triangle ABC can go into the right triangle ADC according to side rule. And from the fact that those two right triangles are can go into each other, we will derive that they have also the same areas. That is to say, the area of this right triangle ABC is equal to the area of this right triangle ADC. The area of triangle ABC is equal to the area of triangle ADC. But we know that the area of this triangle ADC in total equals to 20 plus 10, that is 30 square units. So we can write here that the area of triangle ADC is equal to 30 square units. And from this equation, the area of triangle ABC equals to the area of triangle ADC equals to 30, we derive that the area of triangle ABC equals to 30 square units. From one side, but from the other side, if we define the area of this green shape as x, that is to say the area of this green shape equals to x square units according to our definition, then the total area of triangle ABC will be equal to x plus 5 square units. So from the other side, the area of this triangle ABC equals to x plus 5 square units. So from one side, the area of triangle ABC equals to 30 square units. From the other side, it is equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We will derive that x plus 5 equals to 30. So here we subtract 5 from this equation and finally found out that x equals to 30 minus 5, that is 25 square units. So in total, we actually found out that the area of this green shape equals to 25 square units. Okay, thank you very much.